It is enough with the name. Mohsen Assadi, I'm going to present you the most exciting part of the conference today, which is the real plant out here and the targets with that. My colleague's going to take over after a short introduction. So the background is that the why and what was driving this installation of the large-scale plant with 120 wells drilled around the campus here, and why did we want to push this forward? So obviously, this geothermal heat pump and also the living lab. Let's directly go to the, for those who are still having some energy left, so to say, to follow the discussion here. So it is that the university has a strategy towards green campus, and it has been also targeting the energy transition as the highest target for the university for 2030. And by that, they want to increase the share of the renewable energy and then reducing the CO2 emissions from the campus. So how should we get there? And it was obviously solar cells. It has been placed on the roof, a number of those PV cells, but they came to the conclusion that the geothermal installation should be the one which is going to have the major impact. So using the campus as a living lab was the part of the researchers' contribution to this mindset of where should we head actually, because providing education and research opportunities by using the real installation and real life plants around the campus should be one of the targets, and we did then push forward the research focus. That we want to take advantage of the knowledge developed and also having a cost-benefit analysis. What does make sense in the end of the day? Is it the deep geothermal should we go for, or should we have nuclear plants, or what at the campus to reach our target of green campus? So the idea of drilling different wells with different depths, using different type of heat exchangers in the wells, using different even type of heat pumps to better understand the cost-benefit analysis of what is driving what and what really makes sense. So to realize this, we have established wells with different depths, 2 different depths only, but we're going to have more details about that. We do have also this various type of borehole heat exchanger in collaboration with the manufacturers to provide, let's say, we call it living lab, where we can really investigate different things, generate data for a smart solution. AI was one of those things listed here. So the thing is that you want to run artificial intelligence. I have been working with that in late 80s, so it was not so interesting and sexy then. Now everybody talk about artificial intelligence. The question is, what is driving artificial intelligence? It is data. How do you get data? How you instrument for getting the data which makes sense actually and has impact. All this, let's say, knowledge, domain knowledge connected to the technology knowledge and bringing all that together. It is a process which is going to take time and need a lot of young researchers to contribute to solving that. So providing realistic views of the potential of geothermal means that we need to understand the cost connected to the well depths and the borehole heat exchanger type. There are different types of borehole heat exchanger. You can have a simple tube there, or you can have with turbulator to increase the heat transfer or so, but it costs more. But where is this, let's say, sweet spot? How much should you invest for getting out how much? And when does it make sense, actually? It is about this flexibility, using the geothermal for not only heating and cooling, but also for energy storage during different seasonal periods, during summer storing heat and during winter using that. Of course, education and training of specialized researchers is definitely one of our targets, but also our students to provide this knowledgeable workforce to support the future zero carbon development and implementation. And by that, I'm going to hand over to Fredrik, who's going to tell you more about the details in collaboration with the drilling company.
Thank you, Mohsen. The microphone is working. My name is Fredrik Skaugnes, and I am Mohsen's PhD student, but I am also part of the design team that's responsible for the new energy plant that's being constructed at UiS at the moment. So I have a couple of different hats, and I will try to share my knowledge as best as I can. And this is a fairly conventional geothermal heat pump system compared to at least what has been discussed earlier today, but it's large from a Norwegian perspective, wouldn't you say, Karl Erik?
Definitely. It's, over 120 wells on shallow.
Yeah, so this is shallow geothermal. So let's, I wanted just to start, we're supposed to have a walk around the campus area, but the Stavanger weather is as it is, and the construction site demands shoes, specialized shoes, which we couldn't get for everyone. So it will be a digital walk. Is this, let me see, yeah. So I think we are about here. And what's special about UiS, what I as a building energy systems engineer find very, very, very interesting is that this campus area, all of the buildings within this circle, they are more or less, every building is equipped with hydronic heating and cooling systems, which is not that common in the Norwegian systems. Before I started working with this, I didn't really realize that there were other options than electrical heating. But the fact that that the campus area can utilize geothermal energy is something that we were very happy about. And also, today, we have a decentralized systems. There are gas boilers, electric boilers, some heat pumps for cooling around campus. And somehow someone has been clever enough to, from 1970s until today, connect all of these buildings. So there are pipes in the ground, cold pipes for cooling, hot pipes for heating. So for us now, it's just to build the energy plant and connect everything, and we're good to go, we hope, at least. So that's the geothermal heat pump project. Some words on the demands. Here you see the heat demand curve. It's obvious when you think about it, but the demand changes, and it's for the heat demand is mainly related to the climate, to the temperature outside. And the coldest days, our maximum demand is about 5 megawatts, and the total amount of heating demand is 7,000 megawatt hours per year. For cooling, the demand is most of the year very low, about 200 kilowatts, and then there are some high peaks. These curves are very important for the design of the system, determining the size of the heat pump and determining how many boreholes you need. And let's put up the cooling demands as well. The maximum cooling demand is 3 megawatts. You see that occurs quite seldom, while the heat demand is higher, goes along all the time. But the cooling demand needs to be met. That's an interesting point for heat. A cooling process is basically the removal of a heat process. So if you're doing these calculations to compare various systems, a heat pump system like we are talking about today, you get both heating and cooling from the same unit, and that can help the economic calculations. Here are two different system sketches. Basically, there are two heat pumps. They are the heart of the system. They have been designed to meet the cooling demands of 3 megawatts. They interact with 119 geothermal boreholes, shallow, 300 meters, but also ambient air coolers, and I'll come back to that, why that's a bit interesting. Why? Additionally, there are peak load heaters and boilers, and everything works together in an integrated system. The target is to produce the about 9,000 megawatt hours of heating and cooling demand with a system COP, coefficient of performance, of about 4.3, giving an input energy, electricity and biogas, a combination of about 2,000 megawatt hours per year. And we don't really have good numbers on how much energy is used today in the various in the heat in the boilers and the electricity consumption, but we do believe that this system will give a reduction of CO2 emissions from the campus heating system, cooling system of about 80%. Let's see. This is the duration curve for heating. So I said that the heat pumps have been designed for the cooling demand, but as here what we've basically done is to take the heat demand and sort it. So the largest demand, about 5 megawatts, occurs very few hours per year. And in order to, I remember in the previous discussion not drill, we are playing around with how much energy you can produce from the available cooling capacity in the system without having to drill too many boreholes. Because if you're going to meet that final almost 3 megawatts of heat demand utilizing the heat pumps, you would almost need to double the boreholes, but you wouldn't really get any energy. So we are always looking at how to improve the amount or how much energy you get without having to drill more than you need. Here you see the energy balance. We are taking out more heat from the ground than we are putting back in, but during winter we are taking out heat for heating. During summer we're putting down heat from cooling production. So we're trying to achieve a balance. So you see here this is the simulation of how the temperature in the ground changes as we extract and reject energy. So the temperature, the undisturbed temperature in the ground, the average of 300 meters is about 10 degrees. And then when we begin to extract energy, the temperature quite quickly drops to 4 degrees, and then it goes slowly down to about 0 degrees average temperature in year 50. I think it's really amazing that by putting, it's about 100 liters per second of a brine of ethanol mixed with water. You put down 0 degrees of water, you extract heat, you heat the water 3 degrees. So by heating that water from 0 to 3 degrees, you get 70% of the energy demand at campus. So you don't really need the enormous or the high temperatures in the building heating cooling systems. I would also like to point out what we are looking at now, that in Stavanger, it's never really cold and it's never really very warm. So it's about 6,000 hours per year. The temperature, ambient temperature, is between 4 and perhaps 16 degrees. Then the heat demand isn't that large, and we can utilize the coolers on the roof to either use them instead of the boreholes, because you get the same or better temperature conditions, or you can actually throw heat from the air down into the ground. So we're working a lot to find this balance so that this type of curve will balance itself out even more than it does today. And of course, the higher the temperature is in the ground, the more efficient the heat pump process is, but still we achieve a COP now of about 4, so you get 4 times the amount of energy that you put into the heat pump. Here you see again a map of the campus area. Then I would like to just ask Karl Erik maybe to say a few words. Here you see the whole borehole configurations, the 119 boreholes. We are here. So would you like to say a few words on how the drilling process has gone? And
definitely. To start, we are extremely humbled to participate in this. This is a sexy business, you know. This is a good pilot project, giving data to people, to students, upcoming green energy people, you know. So, and that's a lack we see in the market, that we don't get these data. So I'm looking forward to receive data ongoing here. You see the number of wells is enormous here, 120 wells. So it's a quite heavy logistics in maybe not the drilling. You know, we are the doers, we drill. And that's 300 meters. The bedrock in Stavanger is nice and soft and go quickly. Drilling 300 meters as a day, actually faster in Stavanger. But the horizontal work, the collector and, you know, working on the surface is been complicated here, or more complicated than drilling, you know. So we need to also take care of all the other contractors, suppliers working in the same place. So that's been quite tricky, but we had a good experience from we are doing. Now I'm not sure about number of wells, but at the hospital in Stavanger, it's almost 100 wells there as well. So we had a good experience of the bedrock in Stavanger. So yeah, it looks quite heavy, too many wells, but we had the space, and then we could do that, 300 shallow boreholes.
What's the distance between
it's a bit variations, but you know, trying to be, you know, the thumb is 10 meters, but it will be down to 4 meters sometimes.
Yeah, but I think in this project, the circle represents they've tried to have at least 15 meters in between the boreholes, so from the design plan.
Yeah.
Yeah. So of course, this takes up a lot of space, and as Karl Erik said, you need pipes to every borehole, and then you need to connect all those pipes and bring them from, so the one borehole here, you need to have the fluid come to the energy plant, which is up there. So there's a lot of other equipment as well, which brings us to, let's see, our research project, the Living Lab, as we say. We have 3 main activities. What we call semi-deep borehole, which we defined as 650 meters. Would you say that this is what we believe will become standard maximum in the market in the not too distant future? Would that be?
That's true. As we see the market now, this is a commercial, you know, 650 to maybe 750. It's where the market is just now, and also other equipment, collectors, that kind of technologies. You know, we are talking about cutting costs. We have optimized our drilling rig to meet 600 or 700 meters. But it's not that commercial yet. It's too expensive for us to buy in a new 1 kilometer's drilling rig for this one. So the market is not yet there, but we will see that it's a benefit thing to have both, call it a hybrid field, both shallow and semi-deep boreholes. That could be a very good combination to save areas. But then again, you need to have one rig that can do that the same. And we haven't found that rig yet.
Yes, but at least we decided quite early on that we would like to test that technology. So we decided to establish 2 of those in addition to the rest of the boreholes. Equip them. They were equipped, or were supposed to be equipped, with 2 different collectors with an elliptical shape. So it's a U-pipe with an elliptical shape. And what actually happens There's been a lot of mention of the thermal gradient. When you go down in the borehole at some level, you actually heat the brine within the collector more, and then you send it back up, and it gets colder, and you begin to lose heat to the surroundings. So it's a sort of short circuit of the heat exchanger process. So the plan was to have one with standard thickness and another with a thicker thickness on one of the pipes to sort of try to insulate and to measure that type of heat exchanger efficiency. As Mohsen also mentioned, we have stolen 8 of the standard boreholes and equipped them with different heat exchangers, with a so-called double U. So you basically double the heat exchanger surface. You get a more efficient heat exchanger process, but it's more expensive, more material. And then we are also testing the elliptical in the standard 300 meter boreholes. And we are equipping these with fiber cables, distributed temperature sensing, so that we can measure the temperature all along the borehole through time to see how these respond to our inputs. Here you see our research station, which is going to be built within the plant. As I said, the standard types are just there, connected to the main system, but we have equipped them with energy meters. We're measuring always the flow rate and the temperatures and comparing them with what goes on in the rest of the system. And then for the semi-deep boreholes, the plan is to build a sort of permanent thermal response test system where we reject heat and measure the temperature response and use that to determine the ground conditions. And then at the point in the future, we hope that we could integrate these boreholes as well into the main system, which I think brings us to, the establishment of these semi-deep boreholes has started in January. So we'll give some feedback on.
Yeah, still working on it. We have drilled these, here you see the guys here. We have drilled the boreholes and tried to set the collector, but it stopped at 375 or something like that, due to the fact that the borehole was there was some soft and some hard bedrock in the borehole, so that then you got not controlled drilling. So we faced some cracks and so the collector stopped at the hyller.
Let's see if we can.
Yeah, and we had a film there as well. Now we will do another drilling of 650 meters with a bit bigger diameter and also with directional drilling, controlled.
So basically, to summarize, this the semi-deep drilling hasn't gone as we hoped and expected. We selected the borehole diameter that's usual for this type of borehole with this type of collector. And yes, as Karl Erik said, each and every one of the 300-meter boreholes has gone. It's, as I understood from your people, it's
couldn't set the collector correctly.
No, but in the standard borehole field,
yeah,
it's one of the most successful projects you've ever had.
Correct.
And then when you come to about 300 meters, something changes in the ground. And then the theory is, and we're working on gathering all the information, and we will try to publish all of the results from what went wrong. But something, the ground condition changes. There is some clay-like.
On one side is the clay or softer layers, so that's why it's a bit tricky to set the collector because it stops at the wall.
So if you go around campus now, you actually see the collectors are stuck at in one of them, it's 370 meters. The other, it's 450 meters. So this is my very basic
Here
attempt
you see it.
to understand what has happened. So there are like shelves in cracks, and then the trajectory has begun to change, and then it's just too tight when you're throwing down 2 pipes, and this is a 3rd pipe for the fiber cable. So of course we were quite unhappy, and we are crossing our fingers that the next and the 3rd one will be successful. The idea is to keep the one at 450 meters and do all the measurements and play around with that one, and then hopefully get the new one at 600. Yes, Anders?
Could you lower a camera and take a picture of what's happening there?
We have done that.
You see it there.
The good part here is that we have learned a lot. You know, that's the beauty of it. You know, and we thought it was maybe pushed with cracks, with stones, and we needed to flush it, but there was actually this, as the picture showed.
I don't understand this picture.
So here you're seeing the diameter of the borehole, and this is at about
Just
420 meter. And perhaps, if you take down the light, you'll see. So it should be a sort of perfect circular shape, but there is this crack in the bedrock. As I understand it, I'm not.
But you see the light. If you see in the center of the circle, the yellow circle, you see then hyllen we are talking about. Yes, there. Yeah. And then you see the soft clay on the right side here. And
did you try to run down a whipstock or some kind of edge that would allow to pass by this step?
Yeah, but it's very, very, because the collector, you saw the picture, it's filling out the borehole. So we are struggling to get the fiber as well, the cable with the fibers down there.
So how about an acoustic televiewer and other sorts of logging tools? Because it sounds as if what you have here is it's a problem, but it could also potentially be something useful for later development. Maybe.
But we have a meeting tomorrow, a risk analysis meeting for the next 650 meters. I'm not afraid of just what you're saying. We need to have another hole. But these 2 holes, we will definitely set the collector in a later stage, you know, and find a good solution or a trick we can learn about, you know. But that's the thing happened, and we struggled and used quite much time on this one.
Yeah,
but
I think your guys have been quite frustrated.
Yeah.
Trying to clean the borehole, trying to, and again, I think that's also a very comparing it to oil and gas, that we just don't have the same money to.
No, correct. So that's a good thing with a pilot as well, that we can learn about this, you know, and log it. Also, we see the difficulties in bringing in. You saw the area bringing in big drilling units, because it's hard to move and it's costly instead of a nice and neat one. But then that's also a thing we need to, when we talk to do these machines suppliers, we need to put that feedback back again, and then they need to produce and design a suitable machine.
Have you looked at the lithology from the wells from Ulrich? Because there's a lithological contact over at Ulrich. Not quite, I think, a bit deeper than this, but you may be hitting the same boundary between the shales and the gneiss.
we haven't done so far, but we are bringing along competence from the drilling community at UiS to make sure that we have the knowledge we need to decide whether or not we should go for the third borehole.
Yeah.
But as you may hear, I know quite little about drilling and about ground conditions. So,
but it could be a good indication. You know, we are quite professional on doing shallow drilling, down to 300-400 meters. This occurrence happened after 350-400 meters. We saw a difference in the so that's when we are talking about semi-deep. We need to think about this. We need to check this because we had no indication about this. We did of course, some search on the ground conditions.
Yeah. But it did never happen before with all the wells you have been drilled in different geological contexts.
No, in
100, 200 meters.
No.
Never happened before such
no,
case.
no. We happened to problem setting the collector, but then that's due to rocks and stuff in the borehole, and flushing it out. Then was able to set the collector. So
Very special.
yeah. So the one, yeah. That's the problem. Yeah. We know the strength, the tension of the house there, but it's heavy force, so it's not easy to pull up either. Yeah.
Vibrations?
It could be. So we need to find some trick there to use to get it up and down or just down. No, the water level of this one, I'm not sure.
Oh, I meant in the hose.
In a hose, no.
yes, I think
it's filled up.
they're filled when you.
Yeah.
Yeah.
Liquid. Yeah.
Maybe I missed it. How does the bottom of it look like? Is there some kind of drilling you have this boom that finds its way down? Or?
No, it seems like it's a softer side of one of the side of the borehole.
How does the bottom of your assembly look like?
The problem, and that's a bad thing actually. We are in Stavanger, oil and gas capital of Norway, and we find it hard to find suitable camera to go down 500 meters. But we found one camera coming down to 450 or something, or maybe a bit. But we are not been at the end. At the
Maybe I'm wording it wrong, but what do you put in the hole? How does the bottom of your hoses?
It's just a U-pipe, and then you have some weights on it.
Yeah.
So if you'd streamline that or give it some kind of wayfinding tip, wouldn't it be able to pass this eventually?
Hopefully it could, but we haven't tried. So that's a detail engineering on that kind of problem, of course, and we will sort it out. But it's not anything we can find from our experience before.
No, but
So
but you did use a specialist from Finland who had previously worked in the company designing the collector, so he did think he knew what he was doing. So I think he was surprised by the.
Yeah, I know. Everyone was. That was the. We thought we had plenty of experience around in our big company, both Swedish and Finnish competence, but we were struggling.
It's an adventure.
Yeah. So I'm looking forward to tackle this after we have sorted the 650 out.
Let's see, and those were done. Then just a very brief trip through the energy plant. So here you see from the model, and the building is coming up. here at the moment. It's going very fast. There was nothing on this space a year ago, and it's supposed to start operating in October, November. Here you see the inside of the technical room. The heat pumps, which run on ammonia, they have their own room. There are gas boilers. This is the whole system connected to the boreholes, the evaporator side system. And here you have some electrical boiler and heat distribution system. So it's I think it's about 200 square meters of space you need to produce the heating and cooling as well, in addition to all of the boreholes. The heat pumps you see here in the model, Professor Assadi was there and had a look at them. They have just arrived in the plant. They are in their own room. You don't want ammonia leakage, so that they are contained, and if there's a leakage, they have their separate ventilation system. You see the models, the equipment is coming in, a large glass facade, so that all the students coming down from the bus will be able to see the technical room. We hope to utilize this energy plant in the education. There's a mezzanine where you can go and have a look on everything. We will have screens where you see the energy production, energy consumption, etc. Here we were talking about the pipes in the ground. Here you see the model. Here you see what's going on. So it's spaghetti in the ground, and then when it's finished, you'll just put on the asphalt, and nobody will know that anything goes on.
That's also sexy, you know.
Here you see the roof. Here you see the coolers that we used to reject or extract heat from the air. I'm working on calculations, but I think my current calculations is that we can utilize almost 3 million kilowatt hours from the air. So if you compare that to what you would have gotten from a PV system on the same space on the roof, on 100, 200 square meters, that's quite a lot more. So utilization of air combined with the boreholes here in Stavanger is an interesting concept that we hope will provide a nice energy balance. And again, just to see the spaghetti in the ground there, you need a lot of piping. So that's also one of the important points of the semi-deep concept, that you can reduce this amount, a lot of this piping, ditch work, etc.
Exactly.
So had they been successful, we would have had a very nice paper. Now we hope to describe what went wrong, try to set up cost calculations and do this comparison with if the whole system had been established with semi-deep boreholes instead of 300 meters, how much would you have saved on the piping, etc. Which I think is the final slide. Thank you for listening to us.